Number 3, a skier. So I'm going to start by finding this diagonal distance since the hint recommends it. So we're given this height is 2.5 meters and the angle is 35 degrees. So you can find that diagonal distance pretty easily. Just sine, because you have the opposite and you want the hypotenuse. Sine of 35 degrees equals opposite over hypotenuse. And then algebra happens and you get that the opposite over sine, which makes sense because because sine of a number is pretty much always less than 1. It can be equal to 1, but it's not going to be bigger. And so if you would have to divide, because if you multiplied, then you'd get a smaller number, and the hypotenuse can't be smaller than the opposite. So you find the hypotenuse, and once you have that hypotenuse, then you say the work done by friction is, well, let me write the general equation first. You would, if this were just plain conservation of energy, you would say the initial kinetic and potential energy are equal to the final potential and kinetic energy, which would just look like this. But since we have friction involved here, we have to add or subtract it on one of the sides. And the way I like to do it is say the initial minus the work due to friction equals the final. And some people write it similarly as it's algebraically the same. The initial equals the final plus the work due to friction, which, like I said, algebra, it's the same way, but I like having a minus for friction because it's taking away energy. So I like the first form. So the initial potential energy is 0. It's at ground level. We can pick that as our ground level. The initial kinetic is given because you know the initial velocity and you know the mass. So let me go ahead and plug those in. So kinetic energy initial is 1/2 mv initial squared, all given. Friction, we're about to deal with that. Final potential is mgh. You know mg, what's h? 2.5 meters, that's the height. Kinetic energy final, that's what we're looking for. But I'm going to write it as 1/2 mv final squared. So the only thing we don't know is v final squared and friction. Let's figure out what friction is. So, because of the hint, I'm gonna try doing the definition of work. Force times distance times cosine of theta. So force is, which way is the force? Let's go back to the picture. The force, as the person is going up this hill here, is going to be along the direction of the hill, because friction always does that. And so this is the direction of the force of friction. Can you see? There's the arrow. It just showed up. And the person, it's exactly opposite the direction of movement. So hey, the theta just kind of goes away. Or you can call it 180 if you want. So I'm going to just make it go away. but for those who are mathematically inclined, you can say cosine of theta equals cosine of 180 degrees, that is, equals -1, which is why the work due to friction is negative. But I've actually already taken care of this negative, so I probably, to be really formal, I should have written a positive up here, but I'm just going to say, take out this explanation, because I think what I really did is I took care of it in the picture. I said this is going to be minus because friction's taking away energy. And so I'm just tossing out the cosine because it is along the same axis. So the angle is definitely either 0 or 180. F times D. By the way, if you have further questions on the friction one, just comment on the YouTube video. We have D. We just found it with that trig. It's the hypotenuse that we found in the picture. Now, what is F? Are we given a coefficient of friction? Yes, 0.08. So 0.08. Oh yeah, what is the formula for friction? Mu times normal force. And mu is 0.08. And normal force is, let's see. You can get away with just writing mg cosine theta here. The formal way to do it, which I'm about to show, and you probably should do this most times, is to write out the y net equation. So normal force minus mg cosine theta equals may, which equals 0 because it's not accelerating in the y direction using a tilted axis. And so Fn equals mg cosine theta. And most of the time you can skip that step because there's not really anything else happening in the direction perpendicular to the snow. But it's always good to write out that two-step evidence of Fn. Which I'm taking out now because it complicates the problem in this case. And I'm trying to show the simple example, the simple solution. So this angle, theta, is a different angle than this thing, theta. This theta was the angle between the friction and the movement, and we said that whole term goes away. And this theta is 35 degrees because it's the angle between the so it's the angle of the slope of the snow. That's always the angle that you use when you're finding Fn. So that gives you the work due to friction. You plug that work due to friction into the formula that you had before. And you can find Vf. That's a medium to hard difficulty problem, I would say.